Hello, in this video I'm going to be talking about rotation. Specifically, I'm going to be looking at moment of inertia as well as angular momentum. So starting with moment of inertia, which can be defined as what describes an object's resistance to to a rotational acceleration. So moment of inertia can be denoted by the following symbol. Oh, and before I keep going, I just want to note that I strongly suggest that you go watch the problem to the previous video where problem number 31, as I describe rotational kinematics in more depth in that video, and also this the problem that I'm going to talk about in the later part of this video is a continuation of that problem. Okay, so going back to moment of inertia, which is denoted by this symbol, the formula is the sum of mr squared, which is equal to the integral of r squared dm. So now that we know the formula for inertia and we have an understanding for what the formula is, I'm going to go ahead and talk about angular momentum. So essentially, angular momentum is a measurement of how difficult it is to stop a rotating object from moving. So angular momentum is denoted by the following symbol, and a common formula for this is r, radius or distance, times p, which is essentially just momentum. There are two other ways of writing this formula, which essentially root from the idea that momentum is equal to mass times velocity. So I'm going to go ahead and write them down right here. They are r times mv, which can also be rewritten as m times r. And there's another very common formula that describes angular momentum, which is inertia times angular velocity. And these all can be used interchangeably. So now that we have a basic understanding for angular momentum as well as moment of inertia, I'm going to go ahead and read the statement for the problem I will be discussing. So, a particle of mass m moves counterclockwise around a horizontal circle of radius r, as shown above. The angular speed of the particle is given as a function of time t by w of t is equal to bt, where b is a positive constant and t is greater than or equal to 0. So I'm going to go ahead and draw this diagram up on the board. So we've got our circle and our particle here that's moving in the counterclockwise direction. I'm going to go ahead and label this. This is particle. And then we've got our circle with radius r. And we are also given that the angular velocity is equal to bt, where b is a constant. So problem number 32 specifically asks, what is the magnitude of the angular momentum of the particle about the center of the circle as a function of time? So, we're going to use the formula angular momentum is equal to inertia times angular velocity, since we're given the inertia as well as the angular velocity, or we can find them very easily. So we know that, I'm going to go ahead and rewrite this. Angular momentum is equal to inertia times angular velocity. We know that inertia is going to be mr squared and times angular velocity. We know from the statement that angular velocity is equal to bt. So we can go ahead and plug that in, r squared bt, and then we can go ahead and check the responses, which are, and we see here that option C is written as br squared t, but they're essentially the same, they're interchangeable. So we know that option C is going to be the correct answer for this problem. Thank you.